Welcome to another episode of Dominic Does DIY. As always, like, subscribe, comment down below in order to process that algorithm thing that Google likes if you find this entertaining or useful. It's been a while since I posted a video, but while away, apparently people still are subscribing, and I got up to 50. So Google sent me an email, and I thought I would come back for round 2 and just put out some more videos and see how it goes. So thanks for all those who have subscribed, and hopefully we can get a couple more. And so long as I can keep going, as long as I keep getting subscribers, I'll do my best to keep going here. This is a side gig for me, as I do have a full-time job and then do this on the weekends. But today we will be looking at a common effect in the world that causes possible issues in our circuit design, right? This is like real world stuff that we got to deal with. And what we're going to look at is batteries, right? So we use batteries all the time. You can go on Amazon. You can buy some lithium cells, little battery packs to run your circuitry. And with the technology of lithium cells, we can get actually large amounts of current from power cells, right? Maybe in Amazon you got some energy cells, but they make some power cells. We can pull some serious current from there, like 10, 20, 30 amps from the cell. And usually this is in like brushed or brushless motor designs or other things that you just want to pull large amounts of pulsed current through in order to run whatever, right? But this does cause a side effect on the voltage rail, which we'll discuss in a little bit, because we also need that battery, that same battery that's powering the load, is also trying to power our circuitry, right? Our microcontrollers, our ICs, the other things. And these things have voltage limits on them. So the problem with the battery is in a battery, it has internal resistance. And that internal resistance, while small, doesn't do much when you're talking about, I'm trying to run an LED or a microcontroller, like my max output is going to be 150 milliamps. The internal resistance on a battery is pretty insignificant. You don't really have to worry about it. Even up to like maybe 1 amp, right? 2 amps, you're probably not too concerned about the internal impedance. It really is when we get up to like 10, 20 amps, something like that, where this internal impedance actually starts causing an effect on our circuit that we got to be aware of. So in this, I'm still working on the simulations because I think for this, it's a good thing just to keep with the simulations because they're very effective. And plus, you can see how to use the simulator to hopefully speed up your design so you can work out some little things here and there. So without anything further, let's go ahead and get into this, and I'll show you what I mean with regarding the current draw on the cell. I used to use LT Spice a lot. I still do. I downloaded the P Spice for TI just because the LT Spice has some limitations when you're trying to pull in parts. It's great if so LT Spice is great for if you were using analog devices because you can find all the analog devices in LT Spice, but they're the way that it runs its Spice model, it doesn't necessarily use P Spice outlines exactly. So when you go try to download other P Spice files from different manufacturers, the import gets really sketchy sometimes, and sometimes it's just you can't convert it. So I was working on some TI stuff. So I started using this OrCAD P-Spice, and so it was free through TI, and it works pretty good. So now I can use some TI parts. So usually if I'm working with TI, I'll use this. If I'm working with analog devices, I'll use that. So this time we're just going to be using P-Spice for TI here. Go download it if you want. Check it out. Like I said, it is great for all the Texas Instrument type components because they got the P-Spice models in here, and so you can do more complicated Spice modeling rather than having to wing it and put in substitutions. But either way, what I'm going to do now is show you the effect of that current draw on the cell. So what we got here is we got our 5-volt battery, which we can see right here. And the internal resistance, I'm just going to put at 50 milliohms. That might be high for some lithium cells, might be right on the money for others. It's just the number I'm going to go with on this for the example. You can find that information on the battery spec sheet. And then for my load that I'm going to put on the system, like I said, if it's a brushless design, you're going to be pulsing it. So we're really concerned about pulsing currents on this one, not static pulses. Static pulses, not static pulses, but static current If it's a static heavy current load, you're going to see the same effect, but it's going to be constant, right? So you got to solve it in a different way. This one is going to be dealing with, I have a current pulse. It's coming at about 20 kilohertz I've got right here, and it goes from 0 to 20 amps, right? So this is a 20 amp, 20 kilohertz pulse that we're going to be putting on this system and see what effects that it has on the output voltage itself. So let me go ahead and run the simulation. Okay, so I went ahead and ran the simulation. And so what we're going to do is we're going to voltage probe, and we're just going to voltage probe our voltage source. So you can see here I've got a 100 microsecond delay before this thing starts twitching. But you can kind of see here, even though I've got a 5 volt DC source right here, we would expect me, if I'm just probing that point right there, that it should just be a solid 5 volts. But it's not. It goes all the way between 5 volts and it drops all the way down to 4 volts. If I measure right across the battery, yes, that will remain 5 volts. And so if I take that and I just measure, I do a voltage differential probe and go from there to there, you can see that that one is 5 volts. So my battery is 5 volts. But the problem is because the battery itself is a voltage source plus an internal impedance. So across that entire thing, across the entire battery, we actually see this because you're going to have some voltage drop actually across the internal resistance of the battery. And that's where this sine wave is now coming from, because of the pulse coming from the current source right here, which is simulating the motor. So the problem with this one is the fact that the voltage gets all the way down to 4 volts. Okay, it may or actually may not be. I'm just going to throw this out there for the sake of the video. And we're going to say that what we want on our output is we want to make sure that we stay above 4.5 volts, because we've got some IC on there. I don't know what it is, but it has a minimum operating voltage of 4.5 volts. So if our line, if our battery drops below 4.5 volts, basically that IC will shut down, our system will shut down, and we lose all control, all electronics. So we got to make sure that our battery for electronics stays above 5 volts. So we cannot just connect our electronics directly to this 5 volt battery. So how do we do this? Well, the quick and easy way is to just go ahead and place a capacitor on the output of that, and hopefully the capacitor will keep the system up, right? So let's take a look. Okay, we'll just go and place this wire right here. Place the wire right here. And then we'll just make this beefy. We'll say 100 mic, right? Keep it up. So we'll give this one a go. The problem we're going to have right here. Oh, and then let's also, while we're at it, while we got this open, we'll go ahead and drop a resistor right here. This will simulate our load that we have. So just the electronics. And we're just going to say that, let's say that the electronics is 100 ohms, basically somewhere around like 50 milliamps, right? 25 to 50 milliamps, something like that. So we'll just put a 100 ohm resistor right there. So everything, so right here, these two components right here, this is basically simulating our electronics. These two are our battery, and this current load is just whatever high current load we have, brushless motor or whatever. So now let's take a look and see. So now we got that 100 mic cap. So hopefully when the load gets pulled and the voltage drops, this cap will try to sustain it a little bit. So let's take a look at that. Let's see what that looks like when we run it. So we can see here that really didn't do nothing, right? Maybe it did a little something, right? But not really. And that's because what happens is Yeah, we're charging up the cap, but that cap is also basically able to flow back into the load, right? So this current's getting pulled, it's pulling X amount of amps. That amps that's getting pulled is going to come from one of two locations. You're going to charge the cap, and then it's going to pull some from the battery, it's going to pull some from the cap. And that's why the voltage now is a little bit different at those points, is because we're doing a little bit of feeding the power from the cap in addition to the battery itself. So this isn't going to work, right? We're still dropping below the 4.5 volts on our load on R10, so that's no good. So the next thing is, how can we kind of separate our load from our electronics, right? How is it that we can keep this cap, because we know the cap is charging, so how is it that we can keep the energy of the cap feeding our electronics and not back feeding into the load, right, into the motor? Well, that's pretty easy, because we know there's a discrete device that we can use, and that is just a diode. So if we go ahead and place a diode, and we place a diode right there, then now we have our diode, and we can say, okay, now the capacitor will charge, and when the battery drops below X voltage, well, this side, the cathode side of the diode, will be higher than the anode side when the voltage drops because of the high load. And the capacitor then won't discharge its current backwards into the load, right? So all the capacity will go to feed our load, our electronics, and not actually feed the motor. So let's go ahead and simulate that one and see what happens. So we can see here on the load side, that indeed is doing exactly what we expect it to do, what it was doing before. But now if we take our measurement and we measure our electronic side, we can see that now it's doing what we want, right? A little bit. Each of these divisions looks like it's about 0.02 volts, so 20 millivolts. So we got about a 20 millivolt ripple going on. But it's still, the problem that we have is, even though it flatlines, like once we get the cap charged and it's doing its thing, it looks like it's pretty solid, right? It's regulated pretty well around that 4.15 right marker, 4.15 marker, and it's pretty solid. That's what we want. The problem is we had a Vmin of 4.5 volts. So even though this thing goes into steady state, even though we're able to keep a DC voltage on the anode side, the cathode side of the diode, even though we're able to keep a solid DC voltage on that side, it still will not work because we're still below our 4.5 volt threshold that we need to meet. All right, so even though this is almost there, it's not quite there. So what we really want to do is we want to be able to say, hey, you know what? When this voltage of the battery is higher than 4.5 volts, go ahead and let the battery charge our system, right? But if that battery drops below a certain value, right, then go ahead and put this diode back into it, right? So we want to be able to basically take this diode and put it in and out. We want to put the diode in when it gets to when it's at 5 volts, when the battery's at 5 volts, we want to be able to put that battery in. We want to take that diode out so we can charge the capacitor with 5 volts. But when the battery drops below a certain level, like let's say 4.6 volts, then we want to be able to put the diode back in so that we can prevent the capacitor from discharging its power through the load, right? And we can just keep our output voltage maintained between 5 and 4.6 volts, so we don't drop below that 4.5 volt threshold, right? So that's the crux of what we need to do. We need to be able to take this diode and put it in and take it out, basically depending on what the voltage levels are. So now let's get to solving this problem. So what we want to do is we're just going to go back to our basic one. We have our battery with its internal resistance. We have our current load, but we can't use the diode because the voltage drop on it drops our output below the 4.5 volt level. So we need something else to connect to the 5 volt rail right here. So we need something that connects to there, between there and ground. And so what circuit can we put here that will allow us to have that effect of being able to charge the capacitor to feed the load, but also place the diode in position so that our capacitor doesn't backfeed into the system. So for this particular solution, you are handed 5 100K ohm resistors. You're handed one LM293, which is just a rail-to-rail open drain output comparator, and you're handed one P-channel MOSFET. So using these 7 components, what circuit can we create that will allow us to be able to keep an output voltage greater than 4.5 volts and basically take the place of that diode so that we can have a high voltage output, and the motor, even though it drops, the battery, even though it drops due to the motor load, it will not affect our electronic circuit, and it'll keep that side above our 4.5 limit. So I'll pause the video here if you would like to try and solve it yourself. Otherwise, I will go over the solution shortly. So here's my solution. You may have come up with another. If you did, post a picture of it in the comments down below somehow, img or whatever. But basically, the basic part of this is the comparator. And the idea is that we've got to compare 2 voltage levels, right? We have our battery side and we have our circuit side. And when our battery side is greater than our circuit side, then we want to go ahead and basically connect our battery to the capacitor so we can charge it. But if the battery side drops, right, because it's got a heavy load on it, then what we want to do is we want to be able to disconnect the capacitor from the battery side so that the capacitor could just be used on the circuit side. And if you remember the original circuit, we were like, oh, well, you got to replace this diode, right? So then where is the diode in the circuit? Remember, we took it out, but where is it? Well, that's built into the MOSFET itself. It's built into the PMOS. And so normally I'm not actually using this PMOS as a standard PMOS high-side switch. So normally in a PMOS, you would put the source on the supply side and you put the drain on the load. That's because it's got a body diode. So when you turn the PMOS off, then the body diode would basically block the supply from supplying current to the load through that body diode, right? But this one, I'm using a little bit backwards. What I'm doing is, if you look here, my drain is actually connected to my supply, and my source here is connected to my load, right? So I'm using this actually backwards, which means my body diode is actually facing that direction. So why is it that I flip that? It's still going to work fine. Like, I'm not breaking any of the VGS laws or anything like that with the PMOS. It's just not a non-traditional methodology, right? And so what happens at T0, right, everything is off. So I've got 5 volts on my battery. It goes over this body diode. We'll just say this is a 1 volt body diode. So on my output here, this I've just labeled it V3P6, right? The output of this body diode is now like around 4 volts. That's a 1 volt diode. And so now if we look back, we've got our N minus is tied to our battery, and our N plus is tied to our output. And with the comparator, with the open drain, this particular one, according to the data sheet, is when N minus is greater than N plus, then what happens is that open drain gets shorted to ground. So that's what's happening right now. I got 5 volts here, and through the body diode, 4 volts over there. So my N minus is greater than my N plus, so out gets pulled to ground, turning my MOSFET on. And then that then allows the output of the circuit to reach 5 volts to charge the capacitor. And you also know that I still have that resistor between the source and the gate, right? And that is so that we can actually turn this thing off effectively. If I put this over onto the other side, if I put it over here, On the drain side, I'll get a weird effect because remember, it's all about VGS. And so if this turns off, my gate voltage is going to be more fluctuating than over here. But I want a nice stable off position, right? So I got to put it on the source to gate side, not on the drain to gate side. And so as the battery drops due to the heavy load, then what's going to happen? Well, now the system can react, right? The capacitor, I've got some RDS on here, and so the capacitor can maintain a voltage differential between the battery dropping and this. So what's going to happen is my VN is slowly going to be reducing. Well, it's not slowly, but it's going to be reducing faster than my capacitor between my output. So what's going to happen is my N minus is going to at some point be less than my N plus. As soon as my N plus is greater than my N minus, then no longer will the output be connected to ground, but it'll go high impedance. When it goes high impedance, it'll turn this MOSFET off. As soon as that MOSFET is off, then what's going to happen? Well, that means that this voltage is less than this voltage. So obviously the diode is going to block the capacitor from trying to discharge into the system. And my capacitor can now just use its energy to power the system over here, to power the load on the circuit side. And then the battery will pick back up as soon as the battery gets above voltage again. As soon as N minus becomes greater than N plus due to the battery recovering, the output of the comparator will just pull to ground, turn the MOSFET back on, and we'll go back to charging the capacitor. And then so that's basically the circuit there. If we go ahead and run the simulation on this, let me go ahead and get rid of the diode because it gets confused if I don't. And then we do that. And you can see here, right, all I did was probe my input and my output. And you can see the input, it's fluctuating just like it was before, right? Going all the way down to 4 volts, all the way up to 5 volts. But the yellow line or green line, I don't know, I'm colorblind. So whatever that one is, you can see though, no matter what happens to that output, right, no matter what happens to the input, I should say, the battery, even though it's fluctuating like crazy, my circuit side is a rock solid voltage level, right? So this is doing exactly what we want. The input can do whatever it wants, and my output can be rock solid and not be fluctuating due to the input voltage variances. Now there are a few things with the circuit that are still a little sketchy and need to be ironed out. I really didn't go into details on them. I've done in other videos, but one, I didn't do a tolerance stack up on the resistors here, which I don't know if it will be or not. I don't know if it'll be an issue or not. And two, I do not have any hysteresis built into this comparator. So when things are going, it may or may not be an issue in this particular one. But I'll let you guys decide on either one of those. If either one of those things will break the circuit, and that's just this would be like the first step for me in designing something, and then I would go on to these other things. But I'll leave it here at this point. If you notice one of the tolerance stack ups, the hysteresis in the circuit is necessary, comment down below, let me know, and why it's an issue. Until then, I hope you enjoyed the video and maybe learned something new, or it was a nice refresher, something you may have forgotten. But other than that, have a good one, and I'll see you next time. Thanks for watching.